Let's take a look at the nomenclature of alkenes and at the three-dimensional structures of alkene molecules. You see that carbon has a valency of 4, as it has 4 valence electrons and needs to form 4 covalent bonds to achieve its octet. There's the general formula of alkenes, CnH2n, where n is an integer or whole number. Now if n was to equal 1, that would generate CH2. Can CH2 exist? You'll recognize that hydrogen atoms have a valency of 1, so we can only form single bonds, one single bond to each hydrogen atom, so we don't have enough hydrogens to go around. There is no such molecule therefore as methane. The first member of this family is where we have n equals 2, and an alkene with 2 carbons will be called ethene or ethene, or in America perhaps ethylene. You see the structure or structural formula. It includes a double bond between the carbon atoms, and you'll see that every carbon has indeed 4 bonds attached to meet the valency of 4. And on the right there we have a better representation that reflects the actual shape, three-dimensional shape of the ethene molecule, and here it is with its double bond between the carbon atoms. Note if I turn this to the side that all 6 atoms in the ethene molecule lie on the same flat plane. While single bonds freely rotate, that carbon-carbon double bond does not rotate, and that will be important later in this video lesson. So there you have it, the three-dimensional shape of ethene, C2H4. The so-called functional group is the carbon-carbon double bond. And that's just a reminder of what you've seen there in constructing the three-dimensional molecule. Ethene. Now the next member of this homologous series is propene, and possibly you know this molecule as propylene, P-R-O-P-Y-L-E-N-E. Now to make propene from ethene, we simply add a CH2 group. And you'll see there that between one of the C's and H's in the ethene molecule, I've inserted a CH2 group. And that's true of any homologous series. To go to the next member of the homologous series, you simply add a CH2 group. Let's see that in 3D. So I'm going to put in a CH2 group there, or indeed between any carbon and hydrogen in the ethene molecule, and there's my CH2. So we've now got a carbon chain that consists of 3 carbons connected together, propene. Notice that alkenes have 1 carbon-carbon double bond. The remaining carbon-carbon bonds will be single bonds. So to the left we have a CH2 group, which is double bonded to a C with a H and a CH3. The next or third member of the alkene family, where n equals 4, is butene, C4H8. So what I do is I add another CH2 to what was the propene, and this is what we get. You can see that we have 4 carbons connected together. Between 2 of the carbons we have a carbon-carbon double bond, and between the other carbons we have carbon-carbon single bonds. Always check that every carbon forms 4 covalent bonds in total, and be particularly careful counting the number of bonds connected to the carbons associated with the double bond. So butene. Always identify the longest continuous chain of carbons, and it doesn't matter whether the chain is zigzagging. Here you can see that while it zigzags, the longest continuous chain has 4 carbons. I've placed the double bond, you can see, between the 2 carbons to the left, or at the top. Could I have placed the double bond somewhere else? Could have placed it there. In fact, that wouldn't have made any difference to the molecule, because I could achieve that by simply flipping the molecule over. But there where we see the red arrow, If I place the double bond there instead, that will create a different molecule. So we'll have to look at these separately. So in the first instance, I'm going to place the carbon-carbon double bond there. And it's in the first available space in that 4-carbon chain. Later I'll be placing it between the second and third carbons. You see there we have a CH2. That's the CH2 circled there in the 3D molecule. And below that, what have I got? Well, there I've got a CH3. And in the 3D molecule there's the same CH3 group identified. And of course the nomenclature rules, or rules for naming these organic molecules, had to include a means of distinguishing where the carbon-carbon double bond is placed in this molecule. So where it's in the first available space, it's known as but-1-ene. So instead of butene, we insert a 1 in the middle. In America, I believe it's named 1-butene, so the 1 appears at the front. But in the UK, it's but-1-ene. Now at the bottom left there, this is an alternative. I placed the carbon-carbon double bond in the second space. That makes it the second space counting from the left, but also the second space counting from the right. So again, we could number the carbons just to show clearly that the double bond is in the second available space. So what's this going to be called? Applying the proper nomenclature rules. You can see it doesn't matter whether you number from left to right or right to left. The double bond is going to be between carbons 2 and 3. The double bond is in the second space. Now, there are two versions of this molecule, and there you can see them bottom left and bottom right. Both of these are called but-2-ene, but-2-ene, since the carbon-carbon double bond is found between carbons 2 and 3 in the second space. But let's take a look at a subtle difference between these molecules. If we look at the hydrogens, they are highlighted in yellow, associated with a carbon-carbon double bond. On the left, they are on the same side of the bond. They are both above the carbon-carbon double bond, while on the right, one is above and the other is below. Well, the one on the left is known as the cis isomer, CIS, and we see it here in 3D. You can see the hydrogens are both directed up. We say that they are on the same side of the double bond, they're above, whereas here we can see that the hydrogens are on opposite sides. Back again to the cis form, you can see it's spelled CIS, and this is the trans form. They are known as geometric stereoisomers, and we have a cis and a trans version of these two. They're both called but-2-ene because the double bond is in the second space. And in this molecule we could use either the H's or the CH3s associated with the double bond to identify the cis and trans isomers. If they are on the same side, cis, on opposite sides, we have a trans version of the so-called geometric isomers. You can see the 3D molecules at the bottom. Cis but-2-ene on the left, where the hydrogens are on the same side, or indeed below we have the CH3s on the same side. In other words, either both above or both below. Whereas in the trans isomer you can see that the H's are on opposite sides, one above and one below. And there is in fact a fourth isomer, a fourth way of arranging the atoms. I'm going to swap these around, take the CH3 from there and swap it with the H. Let's do that and see what we get. This is it. Now, the first thing you might notice is that the longest continuous chain of carbons is now just 3. So this is a propene structure with the CH3 group attached to the middle carbon. The CH3 group is known as a methyl group. Highlighted in yellow you can see the longest chain. You could go that way or this way, you still get 3 carbons in the longest chain with a CH3 group attached to the second or middle carbon. So there you see the methyl group or CH3 group attached to the central carbon. So we have essentially a propene molecule where we've replaced a H attached to the central carbon with a CH3 or methyl group. There's the double bond. So what's this molecule called? A propene with a methyl group attached. Methyl propene, or if you like, since the methyl group is on carbon 2, 2-methyl propene. So there you have it, the nomenclature of the first 3 members of the alkene family. Thanks for listening.